Monica Beckwith. Welcome to JAX London. Today I'm going to talk about the guide, the performance engine. I'm a performance engineer, so it's my guide to OpenJDK HotSpot garbage collection. I have another talk tomorrow, and that will be about JIT compilation. So, like I said, I'm a performance person. Pertaining to this talk, my current life involves solving managed runtime performance issues. And in the past, I worked with Oracle Sun and advanced micro devices, where I worked primarily with the HotSpot virtual machine and with the garbage collection and JIT, JVM heuristics. And my last title at Oracle was performance lead for G1 GC. Okay. So the actual title for this talk is I'm going to talk about the OpenJDK HotSpot GCs, and I'm going to talk about the facts, the algorithms, and then some tuning. Okay. So we'll start with the facts. I'll talk about the facts of performance engineering with respect to JVM and garbage collector. I'll also talk about the design considerations. So when you're designing a garbage collector, there are some considerations to throughput and latency. And actually, throughput and latency are the main drivers towards designing a good garbage collector. And then we'll talk about generational GC. All garbage collectors in OpenJDK HotSpot are generational. So we'll talk about what it means to be generational and establish some facts. The next, we'll dive into the algorithms. Now we know about the generational GC, so we'll talk about how the allocations happen and the way. So there is something known as the thread local allocation buffer, which is also known as fast path allocation area, and there are other names. And what that does is enable each thread to allocate lock-free. And we'll talk more about that too. And then after allocation, I'm going to talk about reclamation. And basically, reclamation in the young generation is known as young collection. Reclamation in the old generation is known as old collection. So, and I'll talk about the algorithms, the parallel mark sweep, the serial mark sweep, and then, mark sweep and compact, of course, and then the concurrent mark and sweep, no compaction. Finally, we'll talk about memory leaks, the tuning. Well, not how to tune memory leaks, but how to identify, because we don't really have time to go through an exercise here. But I'll also leave you with tuning recommendations with respect to garbage collectors. So since I mentioned earlier that garbage collectors are designed around the throughput or the latency principle, so how do we tune for throughput? How do we tune for latency? And that's what I'll talk about in tuning. If we have some time, which we probably won't, I'll talk about garbage first garbage collector and how it is different than the other collectors in OpenJDK HotSpot. Okay, so quickly talking about performance engineering, this is what I do. And you'll see glimpses of performance engineering, like application, when I'm talking about memory leaks, how to identify that. So performance engineering has two components. You have the requirements components, which work with when you're doing your system design. You have your performance requirements, your SLAs. You start designing your test plan and developing the test plan. So once you have your performance data, there's the other component, which is called performance analysis. And they both work together, and that's what performance engineering is all about. So let's talk about performance requirements. Like I said about the SLAs, right? So what are SLAs? System level agreements. Your agreements on throughput, your agreements on latency, response time, your agreements on the footprint, how much of your application footprint, not just your Java heap, the entire footprint, and then capacity management. There could also be service level agreements based on availability of your system. Then talking about the analysis aspect of that would be once you have the data, or even when you're doing the run, the performance run, you're monitoring your system under test. What are you monitoring? You're monitoring your utilization, like CPU utilization, memory utilization, any locking going on, so all those statistics. Then at the same time, there's some offline logs that you have gathered, so you'll be analyzing those logs. And then, of course, profiling while the application is running. You'll be doing application, system, memory, all this profiling. Now, pertaining to JVM, specific to JVM, what we do is, first of all, what is a virtual machine, Java virtual machine? We all know about the JRE, the Java Runtime Environment. So the Java virtual machine is a component of the JRE. There is the APIs, the Java APIs, which are the libraries. And then comes the Java virtual machine, which has the runtime, the JIT component, and the garbage collector. Okay, so when you're analyzing, or when you're trying to do JVM performance engineering, you would like to study, analyze, and tune the JIT compiler and the runtime, the garbage collector, the Java API, sometimes even. Depending on where you're working. If you're working for Oracle, you'll be tuning the Java APIs as well. And then sometimes you just do the entire Java JDK, right? So there are different components that you would be either specializing or doing from one day to the other, tuning from one day to the other. What about garbage collection? So garbage collection, you can do online and offline monitoring for the GC, right? You could do heap profiling. You can also, like when you have the GC logs, you can process and plot them, so basically parsing and plotting. And then on the other side, you have the JVM monitoring that's going on as well, because GC is a component of the Java virtual machine. So you would like to do the JVM monitoring as well. And then, of course, everything is the application. Your application is doing all the allocations, right? So then there's also the application profiling. All right, so let's move on to the facts of OpenJDK HotSpot GC. Like I said, throughput and latency are the two main drivers towards refinement of GC algorithms. So let's design a throughput maximizer, okay? So I mentioned generational garbage collectors. All OpenJDK HotSpot GCs are generational. And the reason is that most allocations, new allocations, they die young. So most objects that are newly allocated, they die young. So there's no reason to have a single generation where you would need to collect because it keeps allocating and filling up faster. So what we do is that we have something known as the young generation where most allocations happen, and you age them in the young generation, and then you promote them, the medium-lived objects or the long-lived objects, into the old generation. There's the other aspect of maximizing throughput. We know we have stop-the-world threads, stop-the-world pauses. So what we want to do is be able to do more work, parallel work, during those stop-the-world pauses to kind of quicken the process. So we want to add some parallel threads. Some garbage collectors in OpenJDK HotSpot have concurrent work as well. So you want to add, and by concurrent, I mean it works with your application threads. The garbage collector does its work with your application threads. So if you have the resources, then you would want to add more threads for the concurrent work and get it done faster. So basically, you want to shorten the duration of the concurrent work by adding more threads. Now, if you wanted to design a latency-sensitive garbage collector, you would think about, I should only pause when I absolutely need it. What that means is that most often than not, you'll find that there's no compaction. So compaction means when you're trying for the entire heap, you're marking the live objects, and then you're moving it to the low end of the heap. So it's moving all the live objects. So that's very expensive, and it stopped the world. It may or may not have multiple threads. So sometimes you don't need it, okay? As in CMS, it doesn't do compaction. It does a fallback, single-threaded mark, sweep, and compact, but CMS by itself has no compaction. Then there's the other part of it called partial compaction. So you don't do the entire heap. You just divide it into groups of where you can collect more regions more efficiently, collect more regions efficiently. And that's the principle behind garbage-first garbage collector. It does incremental compaction, also known as partial compaction, also known as mixed collections. Okay, the other part of it is doing work concurrently. So if you're not pausing, how are you doing the garbage collection work? You're doing it concurrently. It works with your application. And in OpenJDK HotSpot, how that helps is that it reduces the, just doing the concurrent work. I mean, there is still, even with the concurrent component, you still have some stop-the-world pauses, but it reduces the time that you would have spent in the stop-the-world pauses. So if you look at the design in OpenJDK HotSpot, this concurrent mark and sweep, the CMS collector, does no compaction and also does concurrent marking, reduces stop-the-world pause time during the remark phase, and G1 GC also falls somewhere here, okay? It does partial compaction and also has concurrent marking in G1 GC. So if I did this green circle as your throughput maximizer, then that would be your parallel GC. It is also known as throughput GC. It is also known as parallel old GC since, I think, JDK 6. And then if I talk about the latency sensitive collector in OpenJDK HotSpot, it's the CMS GC, the mostly concurrent mark and sweep GC. Now somewhere in between there is G1 GC, because G1 GC has partial compaction. G1 GC does have stop the world component. G1 GC is generational, and G1 GC has concurrent marking. So it's right in between somewhere, okay? So fact number 2, like I said, all GCs in OpenJDK HotSpot are generational. So now to show this, how a generational GC works, we'll dive into the algorithm, okay? So just before that, this is what I mean by generational. The young generation comprises of the Eden and survivor spaces, and then there's the old generation. Simple. Most allocations happen in the young generation. So let's go to the algorithms. Let's talk about allocations first. So like I said, most allocations happen in the young generation, and they actually happen into something known as TLABs, like I mentioned, also known as fast path allocation, also known as lock-free allocation. It all means the same thing. So the way it happens, your Eden, which is a part of your young generation, is divided into regions, areas that are thread local. So if you had 5 allocating threads, that's how it would look. So the TLABs would be, so each thread would have its own TLABs. Here I've shown similar sized TLABs. That's how they start. But based on the allocation capacity, so basically between the last GC pause and this GC, and the current GC pause, depending on how many threads I allocate and how often, the TLABs are resized automatically. So many a times you will find some threads having bigger TLABs, some of them smaller TLABs, okay? So now that you have finished your allocation, your Eden is full, and then you can reclaim the Eden area. So you see, we had this bigger Eden, and the live data was only a small sliver of that bigger Eden space. So all that live data is moved into the survivor spaces and then back and forth, and that's how they age these objects. Now let's look at reclamation, because we started talking about reclamation already. So we have the young generation. The survivor spaces are also known as S0 or S1, and they're also known as to space and from space. So same terminology, okay? So now, in OpenJDK HotSpot, the young collection algorithm are similar, and young generation is always collected in its entirety. That means that there is no partial compaction of young generation, even for G1 GC. So G1 GC has the same algorithm similar algorithm as throughput GC as CMS. So CMS is only applicable to the old generation. So basically, young generation is the same. So when people talk about CMS, they talk about G1, it's only about the old generation, okay? And like I said, the old generation has different GC algorithms. All right, so let's talk about the young collections in OpenJDK HotSpot. The algorithm is called parallel scavenge for throughput collector, and just scavenging for all other collectors, but even for CMS and G1, it's parallel scavenge. And it's called par-new, I think, for CMS. But it's the same process. So what I've shown here is your root set, very simplified, only 3. And the way the marking happens is you're tracing from the root set. So the solid green are all your live objects that are traceable from the root set, and the hollow green are, unfortunately, the objects that are not reachable by the root set. So if you just look at the young generation, and this is parallel scavenge algorithm, as I mentioned, the live objects will be moved or copied into the survivor region. For simplicity, I've only shown one survivor. There are 2 survivors, except for in G1, which is just about regions, so you don't have S0 or S1. But anyway, so that's how it'll look. And at the end of the reclamation, your Eden is empty, okay? So it's ready for new allocations. Very simple. Now what about the old generation? So let's start with the throughput collector. So the old generation in throughput collector is multi-threaded, and the entire heap is marked, swept, and compacted. Again, as a monolithic operation, so basically it's done in its entirety, okay? Again, going back to our simplified root set and generational diagram here, and then expanding on the old generation, the way reclamation via parallel mark and compact works is that your generation is divided into regions based on the number of parallel threads, parallel worker threads that you have. So in this case, I only have 4 worker threads, I guess. So that's how it's divided here. And there's the destination region. So one region is assigned as a destination region, and then there can be more than one source regions, okay? So basically what that means is that from the destination region, if you have some space, then the live objects from the source regions will be moved into that as such, okay? Now, the destination region is the next one. So it starts from the low end, and then it goes to the next one. And now I have 2 source regions. So basically, each of those regions are basically your worker threads, right? And then here, and that's how we compact, okay? Again, this is very simplified, but you get the picture, okay? What about CMS? So notice when I say multi-threaded, mostly concurrent, marked, and swept, there's something missing, and there's no compaction. CMS does not do compaction, okay? So how does CMS manage the old generation? There's something called free list. So basically, when the marking and after marking and sweeping, the area that's free is maintained by the free lists, okay? And that's similar. So there's no compaction, so you have this kind of hollow areas, and eventually it could lead to fragmentation. But we're not going to talk about that in this talk. Just something to know about the algorithm, that it's maintained by free lists, and it's not moved around, okay? Okay, there's also, like I mentioned earlier, since there's no compaction, you would eventually have concurrent mode failures or whatever with CMS. And so there's something known as the fallback garbage collector, which is nothing but your single-threaded, stop the world, mark, sweep, and compact collector, which is also known as, if you remember, the first garbage collector in OpenJDK HotSpot known as serial garbage collector. So that's the fallback collector when CMS is not able to keep up with the promotions, okay? In G1 GC's case, tuning can help avoid these full collections, okay? So how does the serial GC work? It's the same as your parallel GC, except for it's single-threaded. So when I spoke about those regions, there are no such regions. There's a single thread doing all the marking and then compaction, just one thread. So it's a long process, basically, depending on the size of your heap and how many live objects you're moving around. Okay, so we'll talk about tuning. The first is memory leaks, okay? A fact is GC cannot eliminate your memory leaks. If your application has a memory leak, GC is not able to do it. GC is just helping your application do the allocations, right? It's trying to give you an area, and then it maintains that area. If you somehow, and I'll talk about how memory leaks can happen, so if you somehow manage to have a memory leak, then GC cannot help you. But GC can help you provide an insight into what's going on. Where's the memory leak? And we'll talk about that. So people always wonder, and they always ask me, so we have Java, which has automatic memory management. How can we have memory leaks, right? So we spoke about how allocations are mostly lock-free out of TLabs. And we also spoke about how reclamations happen after tracing the live data tree reference from the root set. So how can there be a leak? There's a hint right there. And that is what? The root set, right? You're tracing from the root set. So what makes the root set? The class loaders, the classes that are loaded, the static fields, threads, JNI, local, global. And so your leaks are class loader leaks, mutable static field leaks, thread local leaks, JNI memory leaks, right? So your root set is the issue. So if you understand what can cause a memory leak, maybe you can understand how to eliminate that, right? So look for these. So what tools do we have? We have the GC log files, of course. You can plot them, and I'll show you an example. We have heap dumps. We can do heap profiling. We can look at live object retention information. And so those are the options that you can use. Print GC details, print GC timestamps, very simple. Give it a log GC file name, and then parse and plot. Otherwise, you can also use, for the live object retention, you can use JVisual VM, JConsole, Java Mission Control. So here's an example. I had a log file. I plotted it. I made sure that there's nothing crazy, as in like I kind of increased the heap, made sure that the live data set is not, I made sure that we're not having memory issues because of the wrongful sizing, okay? So this is after all that is done. So you see how, so if you look at the yellow zigzag line, that's the old generation occupancy. And the purple is the total occupied heap. And your young generation is just teeny bit, right? That's a CMS GC, garbage collector. So the live data set, you see how it's increasing, and then it kind of reaches, the old generation reaches its full capacity, and you're basically seeing back-to-back full collections. And that was because there was a memory leak in there. So this GC kind of helped, the plotting, the log, helped us identify it. Of course, we did all our due diligence, make sure that there is actually a leak, right? But that's the first way to look at it. Talking about live data retention, you could look at this class loader leak example, and then you see how 9.2 is the first one that's highlighted here. These are simple things. There was also one that has, this was the JNI leak. So the application had only up to 16 gigs or something allocated for the Java heap. But you see the occupancy is going up, the application is occupying 48 gigs, 47, 48 gigs. So when they came to me and I said, we have a leak and it could be the garbage collector, so I was like, okay, give me this, give me that, all this information. Then I asked, how much is your heap? It's like, it was less than 24 or something. And I said, you're saying that your application is occupying 48 gigs? So it's definitely, it's outside of your garbage collector. You're doing something with the JNI, and we ended up doing, but simple things. You could just plot these things and you would find out something is not right. And now that you know what can cause leaks, so you can go and investigate those issues, right? Okay, so we spoke about how garbage collectors are designed for throughput or latency, right? So how do we tune for that? So when I talk about throughput and latency, I also mean, in GC terms, I mean GC elapsed time or GC overhead, okay? So GC elapsed time indicates the amount of time it takes to execute a stop the world event. GC events are stop the world. So what's the amount of time it takes to execute that? So higher the GC elapsed time, the lower the application responsiveness. Because remember, your application threads are stopped. So if you're taking more time during a stop the world event, your application is less responsive. So these are GC-induced latencies. So you want to keep the GC elapsed time to a minimum if you want to tune for latency. The other side of it is the overhead, which is an indication of the frequency. How often do you have these stop the world events? So the more frequent these stop the world events, the more likely it'll impact your throughput negatively. What that means is if you have more GC events, your throughput is impacted, okay? So if you want to increase your throughput, you want to make sure your GC overhead is low. So what is the number one contributor to GC elapsed time? Your copying cost. So when I describe those algorithms, remember we always spoke about live objects, moving live objects. And that's the major contributor. If I plotted, I'm not sure if I have one plot here or not, but if I plotted these times, if I divided all the times that it takes during a stop the world event, you'll see the majority of the time should be copying cost. What about GC overhead? What contributes to GC overhead? Your allocation rate and your promotion rate. So what's the rate of allocation for your application, and how are you promoting? If you have not sized your generations well, then you may be promoting prematurely, okay? So that's what it is here in the recommendations. Size generations, keeping your application's objects longevity in mind. So the faster the generations get filled, the sooner a GC event will happen. Size your generations and age your objects, because we want to avoid premature promotions, okay? Okay, good. So here I've plotted, so I looked at my allocation rates and promotion rates, and you see how the promotion rate, which is the one below, is following your allocation rate. So this was not sized appropriately, and you could tell that as my allocation rates are increasing, my promotion rate is also increasing, and unfortunately, they were using CMS, and what you could see right there on the top, the yellow line meets the purple line, and that's where they had full GCs and they had concurrent mode failure first, and then they had full GCs. So basically, it was not sized appropriately for what they were doing. Okay, so I think am I out of time, or maybe I have some more time? I think I have 10 more minutes. No? Yes? Yes. I have 10 more minutes, I think. All right. So quickly. So we have traditional Java heap. We all know about the contiguous Java heap. We all know about the young generation and the old generation. We all know about how the young generation is divided into Eden and survivors. That's what I've shown here. Right? Everything is contiguous. G1 brings a new concept. It's called regionalized heap. Yes, you have the outer bound. It's contiguous because your heap has to be contiguous. But within the outer bounds, you have free regions and non-free regions. That's it. G1 does not know if, it does know because it's going to, the algorithm knows, but when you're deciding the heap at the start of the JVM, it's just a bunch of free regions. And it can be, any of those free regions can be used for your young generation, your old generation, or your humongous objects. I will not be talking about humongous objects in this talk, but just something to know and research later. So if I put some color into it, you'd see that those non-free regions could have been Eden, old, humongous, survivor. So it could be anything, and it could be laid anywhere, okay? It doesn't have to be contiguous. The generations don't have to be contiguous. So if this was your current heap configuration, and I mentioned that the young generation algorithm in G1 GC is similar to whatever we have seen before for CMS and for the throughput collector. So basically, a young generation is collected in its entirety. So in this case, we have 2 Eden regions and 1 survivor region. So they will be considered candidate for collection, and they will be compacted as such. So some of them got promoted because we had aged them appropriately. So they went into the old generation, and some of them are surviving in the survivor space right there. Now G1 GC has something known as concurrent marking. So after your occupancy, the heap occupancy reaches a certain threshold known as initiating heap occupancy threshold, or heap occupancy percent. I call it IHOP because I forget what it is, so it reminds me when I say IHOP, it's P for percent. Good. So once it crosses the threshold, it starts something known as concurrent marking. So concurrent marking has various phases, initial mark, whatever. We're not going to talk about the phases. One of the phases is called the cleanup phase, in which if there is a region that's full of garbage, in this case, this region in red, this old region in red is full of garbage, and that can be collected during the cleanup phase. So during your concurrent marking, you can see some regions being collected, and that's because they were completely full of garbage. Okay, or full of garbage. I don't know why I said complete. Anyway, so that's how it looks at the end of your cleanup, your concurrent marking. So that region is gone. And now we can start something called as mixed collection. Mixed collections are also known as incremental collections, incremental compaction, partial compaction. And the whole point here is that there will be, during your concurrent marking phase, the regions are arranged based on their liveness, basically per region. And they are arranged from the least expensive to the most expensive regions. By expensive, I mean that it is mostly full of garbage. So if it's not mostly full of garbage, that means it has live data, which means it will be expensive because we do compaction via moving. So our copying costs are going to be higher because we're moving live data. So the less amount of live data, the easier it is, cheaper it is, right? So in this case, during this first incremental compaction, we have identified, out of the 4 regions that we have identified the regions in green, the old regions in green. We've identified that we're only going to collect those 2 because they are least expensive to collect. And of course, during every collection, we have to collect the young generation. So all of the regions in the young generation are going to be also collected. So you have all the regions in the young and a few regions from the old. These are called candidate regions, okay? And then after a mixed collection, the first mixed collection, that's what happens. There could be more mixed collections. So basically you could see more collections like such. So I spoke about the young collections. So these are all your young collections. Right here, your initial IHOP is crossed. So then you have initial mark in green, then you have the remark in yellow, and then the cleanup in orange, and then there's another young collection. And then after that, you have about 5 different mixed collections. Because for this application, the thresholds that were either the default or specified on the command line were such that the first garbage collector thought it appropriate to have 5 mixed collections. So after a single marking cycle, you could have more than 1 mixed collection, and that's what is known as incremental compaction or partial compaction. So if I had plotted this with parallel GC, you wouldn't see anything like that. You would see young collections, and then 1 old collection, and then young collection again, and then 1, because it's monolithic. If I had plotted this with CMS, you wouldn't see any of those things till you see like a full GC or something, right? Because it's mark and sweep, there's no compaction. So that's all I have. And if you have questions, you can ask me, or you could go, if you're using the GC, go to OpenJDK Java.net Or you could do, if you're developing with the garbage collector, go to GC dev, OpenJDK, java.net. Okay. Okay, we don't need that. So cool. Questions, please? Yes?
Why the fallback collector in CMS has to be single-threaded?
Yeah. You have to ask the garbage collector people. I think the whole point was this. We started the OpenJDK, well, the hotspot started with serial GC. The first GC that was introduced, the easiest. Serial GC has the least footprint, easiest to do, there's no parallel threads. So for the longest time, I think up till JDK 6, like I was talking about, even parallel, the throughput collector, had serial GC. And then so these are modular. So they designed a new module called Parallel Old, which employed the parallel threads, like I said, the regions. So it's a lot of work. So now, for CMS, so there are certain things, when you have these modular things, there are certain tie-ins and that's why you would see, even though parallel scavenge is similar for CMS, for G1, and for throughput, but it's called parallel scavenge for throughput, par new for CMS, because the way the tie-in happens between the old generation and the young generation, that's just the way it is. But if you look at OpenJDK forums, Google has mentioned that they have multiple threads for their fallback GC, and I think maybe even Twitter is working on it. So there's other people have done it. You could just do it as well, but I think it's just the way it is because they probably didn't have enough time or whatever. The priorities were not there for that particular thing. But I'm pretty sure somebody's working on it internally too. Yes?
For the two labs, two questions. One is, how is the Eden divided up amongst the threads that are doing this allocation? How is the T-Lab space determined? And what happens when one thread gets to the end of its own T-Lab space?
It gets another T-Lab. So there's a list. Okay, so each region, I mean the Eden region is divided, like I think at the beginning it's 4K or something. I mean, and then, so there are 4K regions and these T-Lab areas. And then as you're done, you will get a new one. Yes, yeah. Because they're just worried about, so allocation is different than collection. Collection happens with garbage collector threads. Allocation happens by the application threads. So application threads don't care about reclamation. So they just care about allocating. So they want to allocate fast. They don't want to have locking going on. So if you had the single monolithic area and everybody's trying to allocate to this monolithic area, then you have to think about locks and everything, right? So, but if you just give each thread, like everybody gets a T-Lab, you get a T-Lab, right? Then you don't have to worry about locking. So because I am my thread and I'm allocating to my area, that thread is allocating to its area, so it's lock-free allocation. So then it's faster. That's a fast path.
Does every thread in the JVM start off with at least one T-Lab?
Every thread in your application.
Okay.
So
yeah,
your application thread, yeah. Okay. So your JVM thread is the main thread for garbage collection. So if your garbage collector has multiple threads, that's taken care of. So when you talk about JVM, those are the garbage collector threads. So application thread.
And
yeah.
Is that true across all the different generational collectors, G1?
Yes. And there's something known as promotion labs as well for the old generation. CMS also has promotion labs, but I'm not sure how it's used because it doesn't make sense with all the free list and everything. So there's lots of improvements done, but then there's, based on the application or based on the feedback from the community, some things were just turned off. For example, adaptive size policy was turned off for throughput collector because it's a smart policy, but we found out that it doesn't work. Adaptive sizing doesn't work based on if your application has different profiles. So all those things are available. So I mentioned just the T-Labs because that works for everything and it's really fast, and so that's the only thing I mentioned. I didn't mention the P-Labs. Okay.
So why don't we use apply T-Labs in old
like I said, we have P labs called promotion labs, which are for the old generation. So you can promote to P labs, and those are for the garbage collection threads. And it does work for, I think, definitely for the throughput collector and garbage, but it has problems with CMS. So we do have them. But there are some other issues with CMS. So it may be turned off. I'm not sure exactly what's, but the P labs are there. So T labs are for your allocating threads. P labs are for your garbage collection threads. So yes, they are there.
You mentioned that a lot of cost is in copying objects around. Does that mean that allocation of very short-lived objects that immediately get swept out of Eden is actually very cheap?
By swept out, you mean the dye? Yeah, it's very cheap.
So as developers, we shouldn't worry about creating lots of very short-lived objects.
You should not, as long as you have sized your generations appropriately. Because remember, as your Eden gets full, that's why I showed that. No, if you're allocating a lot of objects, your Eden is getting full, right? If your Eden is really small, then you have, but even then, it depends on your pastime goals too. So if you don't care, if you're like 500 milliseconds or something, and you don't care, so even if you have these collections, you probably don't care. So, but my advice is that premature promotions are really bad. So you have to make sure that your generation is sized. And it's good practice anyway. What if somebody else comes along and says, no, I just need 10 milliseconds. Now you're like, oh my gosh, I gotta do the whole sizing exercise again, figure out my allocation rate and promotion rate. So once you're doing it anyway, just do it, just try to figure out your allocation and promotion rates and you'll be good. And that helps you with your throughput, right? Okay.
How smart is, I guess it's more with HotSpot avoiding boxing costs? So do you have a method which returns a box type, like do you have a lang integer? Does the JVM avoid allocating that only the int values used?
JVM will allocate everything unless you have escape and so that's a JIT talk. So escape analysis and whatever, then it's on the stack.
Could you repeat the question, please, Margaret?
He said how smart, basically if there's some box type or whatever, how smart is the JVM in allocating it on the heap? So if it has to be on the heap, it'll allocate it. If there are some, that is based on the JVM heuristics. That has nothing, GC does not know about anything. GC just knows that it has, well, GC just knows it has to reclaim once it gets full. And the heap, so the heap management comes with allocation and reclamation. So, I mean, if the JVM is smart enough, then it can avoid it and put it on the stack. Otherwise, it has to be on the heap. There's, are you talking about off heap or something like that?
It is escape analysis, yeah.
Yes, so it is escape analysis. So that's a JIT talk. That doesn't have anything to do with GC. Okay. Any other questions? Okay, you go ahead first.
Since premature promotion is very expensive and also copying most of the time, what's the disadvantage of just setting the young generation very large so that you barely need to promote the older generation?
Depends on your, if you can do that. I mean,
What's the cost of that apart from making them big?
well, if objects die, then the cost is not that much anyway. But
Do you only collect at the end when the Eden's full? Do you only collect when the Eden is full?
yes,
At which point there's a lot to do.
probably not if they're all dead, right? If they're all dead, then there's probably not that much. But I mean, people do that. So if you know your live data set, that's all you need to worry about. So when I showed one of these things, when I showed about how the old generation is getting full, that's your live data set, actually. Okay, so when I showed this, that's your live data set. So sometimes if your live data set is only this much, right, only like say 4 gigs or something, then you can allocate, you can grow your young generation. So and it's not just a live data set, it's also the medium lived objects, the transient objects. So if you can accommodate your transient and your live data set in your old generation, and you have enough heap to spare, enough memory to spare, then you can definitely size your generations accordingly. You just have to make sure that your long-lived and transients are able to reside in the old generation. Okay? Yes?
If you're working from Java 7 onwards, what's the benefits over using CMS in G1 when you've got options to tune your pause time and also the initial heap allocation percentage?
The allocation and the advantage of moving from CMS to G1 GC is that you're not going to have concurrent mode failures. And the biggest disadvantage of CMS are your concurrent mode failures, and people are suffering from them, and they have workarounds around them. There's one of them is one of the workarounds that I've looked at is like something called allocation areas, where they put all the promotions in this allocation areas, and they these are chunks, and then they promote it into the old generation so that you don't have the sizing. I have another talk where I talk about the different sizes, so it becomes like a Swiss cheese. So, I mean, that's the advantage. So if you're suffering from concurrent failures, you're suffering from fragmentation, then you will go to G1 GC and you won't have those issues. G1 GC has so many thresholds, and it scares people because there's so many thresholds, but it also helps you to be able to tune it better. So if you think about, when you're thinking about the old generation in CMS, what are the tuning options? Your tuning options are just limited to generation sizing, right? Is there anything else? Anybody else know about old generation tuning in CMS? Your threshold, your marking threshold, and the generation sizing, right? In G1, you can tune how many regions you want to collect. You can tune how many collections you can have. You can tune what's the liveness per region. You can tune something. I mean, there's so many tuning that you could do that helps you. If your old generation is the problem, first of all, then there's more tuning options in G1 GC than CMS or even throughput collector. Again, throughput collector, what are the tuning options? Your generation sizing, your survivor ratio, your this, that. It's all about the generations, and there's nothing to do with how you could do the old generation. So by having incremental compaction, you're actually able to fine-tune each collection, each compaction cycle. So, I mean, G1 has more tuning, and so if you're suffering from failures, then G1 is the way to go.
So is Java 7 default CMS?
No, up until Java 9, the default is the throughput collector. Java 9, it's going to be G1 GC, the default collector. So people who need CMS, they always have to enable it on the command line. To use CMS GC, I think, is what it is. Okay. Cool. Thank you.